Vepakomma from Motorola. We will talk about the very interesting problem that's about correlation of businesses. If you'd like to join us for dinner, at the usual place, let me know immediately after the talk. I'll be standing here, and please come and tell me your name. Thank you.
Okay, thank you, Professor Zellberger. So this talk is more of a combinatorial optimization intersects an applied statistics problem. So most of the abstractness and the foundations come from the combinatorial side of things, and that's cover most of it. Towards the end of the talk, I'll be talking about the statistical application. And there's a ton of directions, like any problem, that you can go from there, either in the combinatorial side or the statistical side. Go ahead. So let's get started. I'll start with some definitions that will let me go towards the central goal of the talk. So the first definition is about a set function that we call quasi-concave set function. So to get this defined, let's assume some notational standard. So X is the ground set that we're working with. And then let's assume F is a collection of subsets from the ground set, and this is a proper subset, so it does not include X, the ground set itself. It does not include phi as well, the null set. Okay, so that's the collection. So now let's define the quasi-concave set function for any subsets. There's a collection of subsets F. That's a proper subset of the power set, of the ground set. And I'm dropping, so this is the negation, the set difference operator. I'm dropping the null set from it. And also it does not include X itself because it's a proper subset. Like if it was this, it included this. Yeah,
so any collection of subsets that does not include the empty set and does not include the whole thing is invisible.
Yeah, right. So that's the sets. That's the collection of sets F. And for defining the quasi-concave set function, which is the goal, I would take X, y, which are subsets of this collection, and the quasi-concave function, set function, is a real valued function. So it's not even a vector real valued at the point, it's just the real number that it returns, and it's defined on X intersection of Y, it's defined as X intersection of Y greater than or equal to the minimum of g of X, g of Y. So that's the definition of the quasi-concave set function. Just to get a feel for it, that's the intersection. You apply function on it, and that's going to be greater than or equal to the minimum of the function applied on the individual sets that you're working with. Okay. This has some similarities. I don't want to take detours, but this has some similarities with the usual quasi-concave function defined in usual real function space. Anyway, so that's the quasi-concave set function. I will get back to this because I want to go towards another definition that will let me go towards the central goal of the talk. So the next definition is again another set function. It's known as the monotone linkage. I know all the functions I'm using here for some reason have really long names, so it is what it is. I know names of that. So monotone linkage set function. Again, we're talking about the same setup in here. So for let me say S contained in T contained in X, which is obviously again contained in F. Okay, that's what I'm taking in here. And for all xi, and by xi I use that to denote in standard way the single elements of X. So anything with the index is like a single element of the set. So xi belongs to X, right? So for all xi belongs to X set difference T. So anything that's not in T, but it's in here, is what the xi I'm considering. For that, I would define the monotone linkage function as, I would use D to denote it, as d xi comma s greater than or equal to d si comma t. So this is kind of a little weird, but it is what it is, because the smaller set is going to give you the bigger number. That's what it is. If you had a function that satisfies in one way or the other, you can always put in a negative. If it's a positive function, you can still come up with another function that's a monotone linkage function. So those are definitions. Now I'll go to the central goal of the combinatorial side of the problem. And that would later on be applied to applied statistics side of things. So this is the goal.
So you're saying a monotone linkage function is something that does that, not that.
Yes.
Okay.
There could be many monotone linkage
Okay.
functions.
And there's no restriction on the equilibrium of the cardinality of x?
Well, it's a finite set. That's what I would say.
it
It's
is
a finite set.
Okay.
Yeah. You're all in a discrete world as far as this talk goes. No. At least for the talk purposes. So I'll go to the central goal. So this is what we will keep on coming to, or this is the main problem actually, is to find Argmax T within our collection, which is basically the power set, such that I in xi So there's a lot of functions in here, so it's going to be like that. Okay, so remember, t belongs to f, but t, just like in the above function, is to be even more precise in this setup.
How is argmax different than standard max?
How is argmax different than? So argmax returns the argument. So argmax returns the argument t for which this thing gets maximized. It does not return the value.
Oh,
get it
it's the name of the champion, not the echo.
There you go. Yeah.
Clear.
So it's f of x, f of t star. It's not. Well, that's the optimum. So this is going to be t star itself. So that's what we want to maximize. This is the central goal, and you know the simplest thing, but not a very efficient thing, is to enumerate everything in the power set and try everything on both sides. What we're going towards is an algorithm that does this much faster than just doing that. So now I'll move on towards some concepts that I would use to get towards the algorithm for that. So
you're assuming d is computable in unit time, and it's not easier to compute for some things than others?
can you say that again?
Is d computable in unit time, or is it easier to compute for certain things than others?
So this is a very generic framework. As of now, I have no other constraints than what's on the board.
Okay.
You can always, try to apply it in a different situation. So D series. So there's another concept I'm introducing. So the concept I'm doing now is to get towards an algorithm that solves this. So D series is going to be the follows. So since it's a series, I would denote it by SD in the I. It's a series that depends on a choice of I that you take. I would also give an example for this. So X. The condition is that the first element in the series is supposed to be xi itself. So this is going to be how the I decides the D series. That would decide the first element in the set. And it's a complete set of all the n items we're working with. So I'm assuming we're working with n items in the set. Now, xk plus 1, which is basically from 2, and k equal to 1, right, is defined as follows. You want to get this condition satisfied. This is another set that I'm going to define is equal to minimum belongs to x not nxk. So the other thing that I need to define is sk, which is a very simple definition. Just for referring to it, I would refer to this as a starting set. That's what I call it. It's just the name. It's going to be x1, so on, till xk. K goes from 1 till n minus 1. So that sets up. So when you start with k1, you get the first element is fixed based on I, and then k2 onwards, you need to satisfy this condition. Now once you get a feel for that, what I'll do is I will give an example to compute D series when, say, the cardinality of x is 4 or 5 or something like that. So I'll do an example that will give us all the 4 D series. So
When you write S sub d of I colon, that's a definition of S d of I?
yeah, this is supposed to have a equal to.
Okay. So you're saying it's the collection of those satisfying?
So there are a few things here. There's an I that's an input.
Yes.
The series is a series. The input decides the first element. Okay? X is your ground set, like I started with. Sk is another starting set, which basically is going from 1 to k, where k goes from 1 to n minus 1. Now, since first element is defined, to define the rest of the elements, xk plus 1, what you do is you measure this amount that you get from d of xk plus 1 to the starting set, based on whatever k you're going with. So I'll do an example that will make things even clearer. So let's do an example here. So let's assume we have a cardinality equal to 4. So let's just write it down as x. So x1, x2, x3, x4, and say I want to do the D series for I equal to 1. So I will start filling this up. So the first element is going to be x1 itself, because this is equal to 1. And then the second element, to get the second element, you need to do a few computations, which is the follows. You first compute d of x2, comma x1, d of x3, comma x1, d of x4, comma x1, and you see where you get the minimum, because we're talking of minimum. Say, for the sake of the tracing the whole example, say you got the minimum at x3. Let's assume that. If you got the minimum at x3, what's going to happen is your starting set, by the way, you started with x1, which is your starting set when k equal to 1. Now your starting set, s2, is going to be x1, comma x3, because that's where you got the optimum. And then what you do is you again do a few computations. What do you do now? You take d of whatever is not in here that's left out in x. So x2, comma x1, x3, and then you compute d of x4, comma x1, x3, because you're measuring it with respect to the starting set. And then let's assume, for the sake of the discussion, say you got the minimum at x4. So your starting set now is going to be S3 is going to be x1, x3, x4, and then S4 is going to have everything in there in this order. x1, x3, x4, x2, and that is going to be your D series for I equal to 1.
So when you write S sub d of I, what does that mean? Does that mean the I thing in that sequence?
The I only decides the first element in the sequence. The first element. You're starting.
You've given me S1 through S4, but what is S sub d in parentheses I?
So SD of I, the reason for these complicated notations is as follows. D decides what function you're measuring in here.
Yes, so S sub d is the sequence
Is
over
the sequence with respect to I.
Oh, S2 over there would be S sub d of 2?
So these are the SKs. So
Those are capital S.
you know, I could do something like this for you, actually especially for you, and put in a bar in here. So these are the starting sets.
Okay.
Okay, and this is your SD of 1. This is, as well, the SD of 1 is going to keep getting completed after this whole process gets done. So it's going to be x1, x3, x4, x2. All you get is a sequence, that's it, based on your starting condition. Okay, now I'll move to the next concept. I call it the D cluster. And after the D cluster definition, I would have a theorem that will help us settle the question of what the algorithm should be. So we're still going towards the same goal, D cluster. Okay, so D cluster is basically the follows. For any D series for a chosen I, the corresponding cluster, which I would denote by, let's see, by S hat. The corresponding S hat belonging to SK hat for k equal to 1 to n. So basically, SK to the bar is the starting sets. So we look at whatever starting sets are being generated through this process. So this is one starting set. The first starting set was just x1. This is the next starting set, the 3 elements. This is the final starting set. And for each of the starting sets, we will see, for this, the corresponding starting set, which gives us the maximum as maximum of I to x naught sk. This is the starting set, xi. D of xi, comma, starting set. So we're just computing this guy. We can also name this guy as a function, and let me call it m of s, sk. So this is a function of the starting set. So we're computing this part now, and we're looking at whatever maximizes it. Remember, there we had a minimum, but here we had a maximum. Because that's the end goal, the reason the intuition is as follows. The end goal is here. We're looking at the element, the single element, that gives you a minimum with respect to a given set. So this is an element to set function that gives you the minimum, is what we're looking at. But we want to maximize that minimum as much as possible, and you want to choose that kind of a set function. So it's not a function, it's an internal problem of choosing xi, but the main problem, the main goal is to choose the set, which will have that kind of property.
So set with that.
Yes.
Okay.
Just you can name it. It could be the highest worst case scenario or the least best case scenario, however you name it. Example. So basically, decluster, to give an example, I don't even need to write it. It's going to be the starting set that gives you the maximum of m of sk, which is our objective in there. Okay.
So now, just make sure I understand correctly, you're saying do this procedure and then use that as the t in that thing.
The t.
Oh wait, you wrote maximum.
There's no procedure yet. I'm going towards the procedure.
Okay.
This is just a way to shell out sets, if I could call it.
Okay.
People really call it shelling in some areas, I guess. Okay. So now comes the theorem. It's a long statement with a reasonably simple proof, maybe like a 3-line proof. But the power of the theorem really builds up on the amount of structure we put in here. We're using D series, D clusters, all of those linkage functions. That's going to make the proof kind of easier a little bit. And that theorem is going to motivate our algorithm. So the theorem is as follows. Given the D series for all I, and given the starting sets, sk bar, for all k, so you're just gathering everything as an input for the theorem. And now I'm giving a new input for the sake of the theorem, which is, let's call it a particular S hat. There's a lot of S's in here, because there are all kinds of variations of S's in here, so I'll call it S hat, such that, this belongs to, obviously, in some form, belongs to the collection, such that, S such that, there exists, such that there is xk plus 1 that does not belong to the starting set. okay? Because the starting set is going to be computed for amount of k. So you'll have a starting set, say, till x3. Then you're looking for what the fourth element would be, right? So you're looking for an xk plus 1 that does not belong to a particular starting set, and but does not belong to sk. And a better way to say it is xk plus 1, and there is xk plus 1 belong to s, not belong to sk, which is the first element of that kind. Okay? So basically, the S hat is a superset of sk hat. Okay? So it has k amount of elements in it, and the k plus 1th element is the first element that is in here that is not in here, basically. Remember what I'll do is, to make the notation simpler, I'll take this out, and I'll make it a complete series. So that'll be a better way to do it. Only it works both ways. So I will call this a complete. I will call this the D series itself. So give it D series and a set such that. Okay, this makes it more pedantic actually.
Wait, S
Yeah.
of D of, wait, that's S of D of I?
Yes, SD of I. It's the D series
Bar.
studied here. So the reason I did this is for the following reasons. The D series is a complete set with all the n elements in it. It's just in a different sequence. It's in a different order.
Oh, so that's just giving away like a mechanism for scrambling them up with various
Yeah, in a kind of a guided way. There's some reason for that
Okay.
scrambling. So it does that scrambling, and you have k elements in here, but k plus 1th element in here that's not in here is what we're looking at. And remember the cardinality. So the theorem is done. So let me finish the theorem.
That's S of D of I? Is it S hat?
This is SD of I, the D series. This is S hat, which is basically the new set that I'm defining with this condition. Okay. Okay. So now the statement of the theorem is, given all the stuff, along with all those definitions that are defining the stuff, the theorem is as follows. So I've defined this as well. I will point to what it is in there. It's going to be MD of SK SD of I is greater than or equal to MD S hat. Okay, lots of notation, but this is concrete now. The MD, just to recollect, so here, this is the theorem we have. So this is the statement of the theorem given all that. MD is this guy. Or this guy. So both the same things. Okay. And how do we prove that, and what are the implications of that? So let's prove it first, and then I'll get to the implications. The implications are basically we have an algorithm after that. The proof is as follows. So everything comes out from the definitions, nothing coming out of my hat new now. So MD of SD of I is equal to nothing but D of X K plus 1. Okay, hold on. I think I'm a mess. Okay, I will use the starting set cell well, but I'm not changing anything but this guy. So that will obviously be greater, but this is more interesting. That's why I guess I started in the beginning. So we have everything the way it is. The S hat is still there. SK is the starting set as I defined before. I had a bar in here. So we're going to have this statement is an even more powerful statement and generalize it the way we want. As follows. So the function computed over the starting sets, which you got out of this shelling process, is always going to be greater than equal to the function computed over d of x. No, this is going to be equal to xk plus 1, comma, sk var. And also this is, by the statement of the theorem, it says this function computed over the starting sets is going to be always greater than or equal to the function computed over any set, even if it has at least one element that's in the starting set that's not in the other set. So that's like a kind of a global optimality condition for why the starting sets that are being shown out of this process are going to be a smaller search space in which you have the optima. So from 2 part x, we're reducing to just the starting sets, basically. So I'm doing the proof now, which is what this first statement was about. Proof. This is by definition. You can ask me why. So why is it? Because by definition, the starting set was defined such that the next element to the starting set of k length is going to be the next optima. That's how the starting sets were defined. So you're going to get that. And this next statement would be as follows. The dxk plus 1 sk bar is going to be greater than equal to dxk plus 1 comma s hat. Why is that so? That's because of the monotonicity condition of d. The way d is defined, d is a monotonic linkage function, and and since I've said, since we see here basically sk because sk bar is contained in s hat. So by the definition of a monotonic linkage function, you have this. Now all we need to do is be able to say that this guy is greater than or equal to this guy, and that proves it. Because we started with here, and then we got this bound. This is greater than this. And we go from this greater than this. And this is again by definition, because, let me write it down. Purely by definition, you have xk plus 1 s hat is greater than or equal to md of s hat. Why is it? How do you define md of s hat? We define this as the minimum xi that belongs to ground set that does not belong to s hat, for which d of xi comma s hat is going to be the maximum, right? Sorry, this is going to be the minimum. So by definition, you are getting this as the minimum element ever. That's what this is. So this is like the global minimum for this simpler function. So obviously, dxk plus 1 s hat is greater than or equal to this, which proves this. So which is a global optimality condition. So the implication, that is what it is. So this is the algorithm, but I'll write it in 3 steps in English without using symbols or pedantics. So the implication is follows. If you have that kind of a set function problem that you're supposed to combinatorially solve, optimize for, all you need to do is check if the d is a monotonic function, monotonic set function. If d is a monotonic set function, then the argmax-min could be solved by obtaining the d series, which will concretely give you the starting sets, which will give you one d cluster for each d series. And all you need to verify is check, basically check, which of these sk bars, which of these d clusters give you the maximum required, and that's the solution. That is the global maximum. Now, is there one global maximum? Not necessarily. There could be multiple global maxima. But this approach would still narrow down all the global maximums within the sk bar subset, subclass of sets. So you can shell out all the global maximums. Yeah.
I'm just a little confused about the theorem, sort of how we're respected. You're saying we take our starting set we've constructed from doing this. We take sk, I'm not sure that lives. That's from our starting, that's the kth guy in the starting set?
This guy?
Yes.
Are the starting sets.
I thought sd of I gives us a starting set.
sd of I gives you the d series. So, so you start with a choice of I.
Yes.
that will shuffle your
Yeah.
inputs in a very guided way.